I'm going to be talking mostly about QUIC, some about how QUIC can be used with WebRTC data channels, which does not yet exist. So I should preface this entire talk with all of the relevance to WebRTC is a future concept. So just like, but it's exciting, but it doesn't exist yet. So I should say that now. What is QUIC? QUIC does exist. It's a reliable multiplex transport over UDP. It's always encrypted. It's designed to reduce latency, particularly on the web, and particularly for connection establishment. It runs in user space, so we can upgrade it pretty rapidly. We don't have to depend on the kernel upgrades and the multi-year cycle that might require. And it's open source in Chromium. So everything I'm talking about here, you can look at. It's in chromium.org. It's all there. We're running pretty much the same code, minus like a 1 week lag at Google that's in the Chromium repository. Okay, so where does it fit today? Right now, it's used kind of as an HTTP2 substitute inside Chrome. There's a bit of a shim to kind of do a little bit of translation, and the rest of it is QUIC. So QUIC handles the multiplexing of HTTP2, handles prioritization, handles flow control, handles reliability, handles a lot of things that TCP does on top of UDP. And that's where its relevance to WebRTC is particularly strong, is where it sits in the stack is very similar to where SCTP and TTLS sit today for WebRTC. So QUIC has congestion control and reliability. It builds on decades of experience with TCP, so we really tried to implement all the best standards for TCP. It's a very modern style implementation, but it's an entirely new implementation. And there are some benefits to the new implementation because we're not stuck with the exact implementation choices that they made in the kernel 5 or 10 years ago. As I said, it incorporates best practices, including a variety of things which are sufficiently new that they've been talked about and written about, but haven't actually become RFCs yet. But it also adds some signaling improvements that can't be done in TCP. It took, I think, over 20 years for TCP to roll out SAC, which is selective acknowledgement. It turns out this is absolutely critical to making real-world networks work, but it took 20 years for it to roll them out. We can make changes in months. So an example is our loss detection tends to be much better because we don't have retransmission ambiguity. When we retransmit something, we know which one was ACT. But we also have a lot of flexibility going forward. So we can improve our signaling, we can change our signaling, all things that are essentially impossible with existing TCP, at least in the timeframes that are relevant to us. So a huge feature of QUIC is zero RTT connection establishment. That means that you can send the connection establishment request and the first user data, the first request, for example, in the case of HTTP, all in one go. So you send it like one packet after the other. This is kind of similar to TCP's TFO, the nice TCP fast open as it's referred to. The nice part is, number one, this actually works in the real world. No one really has managed to deploy TFO very widely in the real world because, again, TCP is really hard to change and hard to get new features deployed. But it also does the security handshake as well as the kind of connection level establishment all in once. And this works at Google about 75% of the time. So we're taking commonly 3 RTTs of connection and establishment down to 0. So it's a huge win, especially for mobile connections and especially where the RTT is large. So QUIC is always encrypted. The security is comparable to TLS. It actually uses the 2 ciphers that are available in TLS that are proven to be actually modern and secure and not hacked. So in some ways it's better than TLS because TLS still supports some older ciphers which are a little bit questionable. It has a more efficient handshake. It turns out the server CPU costs are a little bit lower on the handshake side. So resuming these connections is very cheap on the server side as well as on the client side. Has IP spoofing protection. So even though it has zero RTT connection establishment, as a way of making sure that the person sending the packet is really that IP. That prevents DDoS and a variety of other issues. And it's already inspired TLS 1.3. So I'm sure that'll take a few years to get standardized. But TLS 1.3 includes a zero RTT handshake. And it's worth noting that, we've kind of managed to feed some technology from QUIC back into TCP already. So what can we do with QUIC and WebRTC? Well, QUIC shares a lot with SCTP and DTLS, which is exactly the standard underpinning today for data or peer connection. So it's a multiplex protocol. It supports a huge number of streams. I think it's by standard 4 billion, but I could be wrong. It could be larger. It has flow control on both a stream level and a connection level. And so that's kind of a requirement for a modern protocol. It's always encrypted, as I mentioned before. And it has out-of-order delivery. So unlike TCP, you can get out-of-order delivery semantics, and you kind of choose like what's in order and what's out of order. So first, connection establishment would be the big benefit to DataChannel. Currently, it's 4 RTTs in the typical use case. Obviously, going to 0 is a huge difference, especially for applications such as actually making like voice calls on a mobile. This changes kind of the whole user experience. It also has reduced framing overhead. SCTP and DTLS, because they're layered one on top of each other, actually has a fair amount of framing overhead when you deal with smaller, payload sizes. So if you do attempt to do something like audio, which usually you wouldn't do over data channels, but if you did do audio over it, you would have a fairly large amount of overhead, kind of on a per packet basis. It also has improved congestion feedback. I actually work very closely with one of the people who standardized SCTP, and he was complaining that a lot of things in SCTP were great, but there were certain things where QUIC really had a much better choice of implementation. And part of that is because he's now on our team, and he can say, no, we did it that way. That was the wrong way. You should do it this way. So how would you map data channels into QUIC? So QUIC right now is really oriented around kind of an HTTP2 semantic with reliable delivery. But it has all the features we need to do a wide variety of applications. So by default, it's ordered. QUIC streams implement ordering. But WebRTC also needs unordered delivery. But because we have lightweight streams, we can create just thousands and thousands of streams. I mean, you could even create a stream for every single audio and video frame. And I think it turned out you only ran out of them after like a day and a half. So, they're very, very cheap to create. And these allow you to easily do unordered delivery. And so you can kind of choose what's ordered and what's not. And that's really a critical feature of DataChannel. It's also, you can make it reliable, as it is typically used today, or it can be used unreliably. So as soon as you cancel a stream, no more data will ever be sent on it. No more data will be retransmitted, and that allows you to implement policies like max number of retransmissions or max time for retransmission. Again, standard features of DataChannel. So how does this look in terms of kind of an architecture diagram? We have the DataChannel API on the top. Kind of as similar to HTTP2, there's kind of a bit of a shim to adapt DataChannel over to QUIC. And then there's on the left-hand side, there's SCTP and DTLS, which QUIC is replacing. So it's replacing both the security layer and the streaming layer all in one. And then from then on, it looks fairly similar. So how could QUIC be improved for WebRTC? Today, there's still a few things that could be a little bit better. So QUIC has cancelable streams, but they're not fully unreliable. I mean, there's a little bit of overhead. There might be some optimizations to be had for just saying this stream is completely unreliable, set it and forget it. FEC. So QUIC currently has forward error correction. It's a fairly simple XOR-based approach. That means you can only recover one packet at a time. For audio and video applications in particular, media applications, it would be very helpful to have something that was more of a network coding type forward error correction, if you're familiar with that. So media-friendly congestion control. QUIC and Reno are terrible choices for real-time streaming media. if you're trying, or even to be compatible with real-time streaming media. They will, if possible, bloat a buffer to all get out. And so even if you had a data channel on side of a real-time stream, you need to be conscious of what congestion control you're using for both, because you could inadvertently cause yourself a lot of extra latency in your real-time media stream by using the wrong congestion control, in your data channel. And then connection migration and multipath. So obviously, we talked about connection resumption a little bit earlier and kind of resuscitating state. But it would be awesome if a mobile device could migrate between Wi-Fi and cellular easily without having to do anything special on the mobile carrier part. So what's next? There's a lot of future work, improvements to forward error correction on the QUIC side, connection mobility, as I just mentioned, multipath, and quite a few congestion control improvements. So all the things that I said we're missing are sort of lining up with all the improvements that we're planning on doing in QUIC already. But in terms of WebRTC, we haven't even got to the point we have kind of an initial implementation, so we're still at the testing phase. We're making good progress. We need to actually run a real experiment on real applications and make sure that all of the connection establishment benefits and the other benefits really bear fruit. And then it would be awesome to experiment with MediaStream API and actually see if we can do a combined unified transport for both the audio and the video and do everything over one. But that's a ways down the road. So right now, it's all open source. There's an HTTP 2 test server in Chrome. We're working to get support for Apache Traffic Server, the clients in Chromium. Google Android and Google Chrome support it. And it's been presented at the IETF, and this summer we're doing a barb-off. So there's definitely a plan to move this towards standardization. And the plan generally is that we're going to probably standardize the crypto aspect as TLS 1.3, and then standardize the transport itself separately, and then different applications such as WebRTC, HTTP will use it. So a quick summary. QUIC is reliable and multiplexed. It runs over UDP. It's always encrypted. It's designed to have lower latency connection establishment. It can have forward error correction. It changes all the time. Well, less so now, but we can definitely iterate rapidly if we need new features. And it's all designed to be open source. And you can find out more on chromium.org. So feel free to take a look at the docs, both on crypto framing and the transport itself. So, questions?
What about, maybe you mentioned this, what about that other TCP quality, fairness?
Oh, yes. So there we go. We hit it right in the slides. TCP, so our default congestion control is TCP QUIC, which is the same congestion control algorithm used by Google in the Linux kernel, and is the default in the Linux kernel ever since 10 years ago or something. And so it's designed to be, at least in modern day, pretty much exactly identical.
Did you borrow over any of the other SCTP pieces like multi-homing and resiliency coming from that?
The SCTP parts? No, I don't think so.
You know, what CMT, I'm assuming, you talk about Janardhan Iyengar is your colleague who
Yes.
worked on this RFC.
Yes.
He's my colleague from grad school. That's why.
Okay,
I
well,
know
then,
about this
okay,
work.
now we're getting into SCTP questions.
Yes.
We know.
No, but did you borrow any of that here? Because those did make sense, but it never did see the light of day with SCTP. I work in telco now, and SCTP is used to diameter.
Right.
But it has never really been used there. So
Yeah,
those were that's what I'm trying to understand. Maybe we'll take this offline.
Yeah.
Yeah, if you don't mind, maybe we have time for one other quick question from Les. If you mind, use the mic, please.
Deployed is QUIC actually deployed on anything that we can see on the web yet?
Actually, it is. So it is currently approximately half of the traffic between Google Chrome and Google. So it is quite a bit of traffic. I skipped those slides because they seem less relevant to WebRTC, but yes, it is a good amount of volume.